In this video, we will try to evaluate the integral from 0 to infinity of x squared over 1 plus x to the fourth power. And to do that, we'll use the residue theorem. Okay? So here in this case, we will try to do a counter integral around the upper half circle, okay, which will go from r to negative r, okay, and so we will say that our counter integral around this half circle will be equal to our two paths, our path gamma 1, okay, which is along the real axis, and our path gamma 2, which is around the arc length, okay. So it will be the integral around gamma 1 f of z dz plus integral around gamma 2 f of z dz, okay. And so the residue theorem states that the integral around this counter integral is equal to 2 pi I times the sum of the residues, okay? And so the residues basically is if we divide by 0, so we will set x to the fourth equal to minus 1, okay, and solve that. Minus 1 is equal to e to the pi I, okay, so plus k times 2 pi I, okay, because it repeats, and so we will get that x is equal to e to the pi I plus k times 2 pi I over 4, okay, and k ranges from 0 to 3, okay, that should be a 3. If you look at our counter integral, you will see that only the two first residues are in our domain, so for k equals 0 and k equals 1, okay. So our first residue will be given by just e to the pi I over 4, and our second residue will be given by e to the 3 pi I over 4, okay. The other one are in the bottom half plane and they aren't in your domain, so we don't care about it, okay? And so the residue theorem states that our integral is equal to 2 pi I times the sum of the residues, okay? And so our first residue basically will be it will be x squared over the derivative of the denominator, okay, so it's x squared times over 4x to the third power, and so that is equal to 1 over 4x, and now we can just plug in our x1 and x2. So for the first case it's 1 over 4 e to the pi I over 4, and for the second one it's 1 over 4 e to the 3 pi I over 4, okay. I think this should be correct, and so the residue theorem states that our integral around our domain is equal to 2 pi I times the sum of the residue. So it will be 1 over 4 e to the pi I over 4 plus 1 over 4 times e to the 3 pi I over 4. Okay, and so we can factor out 1 over 4, which will give us pi I over 2 times 1 over e to the pi I over 4 plus 1 over e to the 3 pi I over 4. Okay, and now the our contour integral is equal to these two path integral, so over gamma 1 and gamma 2. And so basically our integral gamma 1 can be seen as the limit where r goes toward infinity, so r is the radius of our half circle, of the integral from negative r to r of our function. Okay, and so that gives us the integral from negative infinity to infinity of our function, which is just the function we had at the beginning. Okay, and our second integral will just give us 0. Okay, and why? Well, we can use the following proof. You can use, basically it's called Jordan's lemma. It states that our integral around the arc length when r goes toward infinity, it will just give us 0. And basically what we can do is we can set z equal to r to the e to the I pi t, okay, where t ranges from 0 to 1, okay, that's our circle. And so we can plug it in our integral. We'll get r squared e to the 2 I pi t to 1 over r to the 4th e to the 4 I pi t dt. Okay, and now what you can do is basically states that this value here is more than the arc length. It's smaller than or equal to the arc length, which is p pi times r. Okay, so distance, so the length of our arc basically, times r squared over r to the 4th minus 1. Okay, and so you get pi over r to the 3rd power over r to the 4th minus 1. This can be proven, but I won't do it here. And so here you can see that you have a bigger power in the denominator. And so if r goes toward infinity, then this value here will just give us 0, okay? And so our integral is smaller than 0, but it also needs to be bigger than 0 because it's a length. And so basically the integral around gamma 2 will give us 0. Okay? So we can just say that our contour integral will be equal to our integral around the real axis, so around gamma 1, which is just the integral we had to solve at the beginning. Sorry. And using the residue theorem, we came up that with the value pi I over 2 times 1 over e to the what was it? Pi I 4. Basically, I can just write e to the negative pi I over 4 plus e to the negative 3 pi I over 4. And so this is the result of our integral. Okay, so basically you do a contour integral. Generally you do it around the upper half circle. Then you can prove that, or just assume that the integral around gamma 2 goes to 0 when r goes toward infinity. It's called Jordan's lemma. You can look it up on the internet. And so we will be just left with the integral from minus r to r when r goes toward infinity. And, oh, I made a mistake. It's the integral from 0 to infinity, not negative infinity to infinity. And so the only thing you have to do, in this case when it's from 0 and not negative infinity, you have to multiply your final result by, you have to divide your final result by 2. Because you just go from 0 to infinity and not negative infinity to positive infinity. So here we won't divide by 2 but by 4. Sorry, that's a big mistake. Or a small one, I don't know. And so yes, now it should be correct. And thanks for watching.